All right, let's talk about Taylor polynomials. But before we get started, I want to make sure that you watch that video on Taylor series by 3 Blue 1 Brown that's posted on Canvas. Be sure to watch that first because it does an incredible job of introducing the concept and the motivation behind Taylor polynomials and Taylor series. And the animations are amazing, and it does a way better job than I could ever do in any video like this. So be sure to watch that first. So what is the idea behind a Taylor polynomial? The idea behind Taylor polynomials is to find a polynomial function that approximates a non-polynomial function near a point. Now, why would we want to do that? Well, first of all, polynomials are just way easier to work with in general. But there are also some relationships that are difficult, if not impossible, to model with elementary functions, the functions that you know of. Addition, subtraction, you know about logarithmic functions and exponential functions and sine, cosine, tangent functions. But there are relationships that are not easily modeled or impossible to model with those elementary functions. But with Taylor series, we don't have to let that stand in our way. So what we're trying to do with Taylor series is we're trying to take a polynomial and match its derivatives to another function. All right. So in the video by 3 Blue 1 Brown, he goes through the process of doing that with cosine of x. Now, in the end, you're going to have a formula. I'm going to give you a formula, and you'll kind of do this formulaically. You won't, you won't derive the coefficients every time because you have a formula for the coefficients. But I want to make sure you understand that this is just nothing magical about Taylor polynomials. All we're doing is trying to match the derivatives, right? We're trying to find coefficients for a polynomial that match the derivatives of another function. So what we're going to do in these first 3 examples is go through the process of deriving those Taylor polynomial coefficients for the function e to the x. Okay, we're going to go through that same process that they went through in 3 Blue 1 Brown, that video. They went through for cosine. We're going to do e to the x. All right. So first thing we want to do is we want to make sure that the value of the function matches, right? So we want p of 0, right? Because we're modeling near x equals 0. We want p of 0 to equal f of 0, f being the function e to the x. All right. So we know that f of 0 is equal to e to the 0, which is just 1. Okay. Now, p of 0, we can look at p of 0, right? P1, we'll call it p1 of 0. If we put in the x equals 0, we get c0 plus c1 times 0, right? c1 times 0 is just 0, so this is just c1, or sorry, this is just c0, and we want the values to match, right? So c0 now has to be equal to 1. All right, so we got c0. The next thing we want to do is make sure that the derivatives match. Okay, so let's take the derivative of e to the x. What do we get? F prime of x is equal to e to the x, right? The derivative of e to the x is e to the x. So f prime at 0, right, is equal to e to the 0, which is 1 again. All right. Now, what's the derivative of this polynomial, this generic polynomial? P1 prime of x is equal to the derivative of the constant is 0, and then the derivative of c1 times x is just c1, right? And we want the value of the derivative to be the same as we want the derivatives to match at x equals 0. So that means that p1 prime of 0 is equal to c1, which has to match the value that we got for the derivative at 0 for e to the x. So we want that also to be 1. All right. So now we know C0 and we know C1, and we can write our polynomial. So P1 of x is equal to, it's just going to be 1 plus 1 times x. So just 1 plus x. Okay, that's pretty simple, right? It's a pretty simple formula that models e to the x. So we might want to ask, how well does that approximate the function at, say, some small value near 0? Okay, so here's 1/10. So we can take a look at and compare the actual value that we can get from our calculator, and then compare it to the value that we get with our polynomial approximation. So P1 at 0.1 is just going to be 1 plus 0.1, because this is, x is equal to 0.1, right? And so we get 1.1. All right. Now, let's take a look at f of 0.1. All right. Well, that's e to the 0.1. Now I can put that into my calculator. You might wonder, though, how does my calculator know what the value is of e to the 0.1? And we'll maybe talk about that. If I put this into my calculator, I get 1.105171. Okay, so that's not too bad. If I look at the difference between the two, if I take f of 0.1 minus the polynomial at 0.1, it turns out to be, 0.005171, which is less than a 5% error. Okay, if you compute the percent error, it's less than a 5% error. That's not too bad. Okay, but can we do better? And that's what we're going to talk about in the next example. We're going to add another term and try to do better, try to come up with a better approximation for e to the x using a polynomial.